Great, thank you. As you know, my name's Eric Niebler. I work at Facebook. Been there for 4 years now, working mostly on C++ standards and libraries. Before that, I worked for myself for about 13 years. Part of that time, I kind of drifted. I was a nomad. It was fun. You can ask me later about what my experience was like living out of a suitcase for a couple years. While that time, I was independent consulting, mostly for Boost libraries and things like that. I've been on the committee for about 13 years, so feel free to ask me any questions about the committee in case you didn't make it to grill the committee last night or didn't get a chance to ask your question. And before that, I worked for Microsoft. So I've been in the industry for a while. I've been doing C++ for about 20 years, which may be older than some of you. But maybe not, I don't know. Anyway, what I'm going to be talking about today is asynchronous abstractions. So you guys are all familiar with the C++ standard library, with containers, with iterators and algorithms, and how iterators are the central abstraction that let algorithms and containers work together generically. And it works very well for synchronous code. C++ is increasingly becoming an asynchronous programming language. So if you want to target the full computing power of a modern desktop station, including GPUs, and including heterogeneous computing like that, then you need to write your programs asynchronously. Otherwise, you're only targeting about 1% of your computer's hardware. Unfortunately, in standard C++, there is no portable way to access the full computing power of modern desktops. The committee wants to address this problem. So they're doing some fundamental rethink about asynchronous abstractions. Those of you who are familiar with the standard library knows there's some support in the standard for asynchrony. There's std_async, there's std_future, there's a bunch of low-level lock-free primitives, there's mutex and locks. And so you might know that everything that is in the standard library is either extremely low-level, expert-friendly, and hard to use correctly, or it is extremely slow, and I'll talk about that, or it's broken, or some combination of the three. So the committee really wants to rethink async and to do it right, and to come up with high-level abstractions that are usable by mere mortals and that are efficient and composable and powerful. And so I'm going to be talking about the committee's search for the async equivalent of the iterator abstraction, the thing that's going to let us glue together all of our asynchronous programs efficiently and powerfully. So I put this presentation together with David Holman of Sandia Labs. He asked that I have this slide in there. So you can all see Sandia Labs. Okay. So the goals for asynchronous abstractions in C++, it's that we need an abstraction that is composable, that has low abstraction overhead. It works with coroutines, fibers, threads, what have you. And that's also extensible to multiple execution environments, that is both parallel and concurrent. You should be able to target thread pools. You should be able to target GPUs, networked computing resources, etc. Okay. So that's where we are trying to go. First, a quick disclaimer. Nothing I'm presenting today represents official views of this WG21, that is the C++ Standardization Committee. All of this is quite tentative, and it's just how the ideas are evolving in current committee papers. Also, I use C-style casts. Viewer discretion is advised. I'm going to run through some really quick background information about what concurrency and parallelism is. They're not the same thing. So when I say async, I mean both concurrency and parallelism. With concurrency, there are multiple logical threads of execution, multiple tasks that are going to execute at the same time, and there may be some dependencies between them. Maybe one task is blocking on a mutex that the other thread of execution is going to try to acquire. So they are communicating with each other through some mechanism. Parallelism, on the other hand, you have multiple threads of execution and they don't communicate with each other. So a smart scheduler might decide to schedule things in a different order because it knows, because this is parallelism, that there's no interdependencies. So, like I said, scheduler, if you give a whole bunch of parallel tasks to a scheduler and say go, the scheduler might do something smart. It might schedule things in a certain order that it knows to be optimally efficient. Or it might just decide to order them all serially, because it can do that because it knows there's not going to be any deadlock because these tasks are independent. Parallelism and concurrency are actually, they live at opposite ends of the spectrum. A scheduler with concurrency has far less freedom to schedule things because it doesn't know about the inter-task dependencies. Whereas parallelism, a parallelism scheduler has all kinds of freedom and power to reorder things. Serial is right in the middle of that, right? So there is a certain amount of freedom and a certain amount of power that's allotted to serial execution. So parallelism is more universal, you could say. If you use concurrent features to express parallelism, you're imposing overhead because you're taking freedom away from the scheduler. Right? So the scheduler cannot make the same choices about reordering things because it doesn't know that actually there's no interdependencies and it could be doing something smarter. It's because the programming model is not restrictive enough. Okay, so in C++17 we got parallel algorithms. Why are they fast? Right, because when you pass the par unseek execution policy into a parallel algorithm, you are making a promise to the compiler, right? Scout's honor, I am not creating inter-task dependencies in these parallel tasks. Right, Scout's honor. And you can take advantage of that information to do something smart, right? In other words, you are communicating the full structure of the algorithm's task graph to the scheduler before executing the algorithm. Okay, and that's important. Okay, with that background information, I'm going to pause button on that. We'll come back to it later. And I want to talk about senders and receivers, which are the asynchronous abstraction that we are proposing for the committee. Now, let's rewind and talk about standard, futures, and promises. I maintain that promises and futures are a bad asynchronous abstraction from the point of view of like efficiency and basis operations. So let's look at a really stupid example of an asynchronous algorithm. And again, apologies about some of the examples in this presentation. I give examples of asynchronous algorithms and they're not very realistic. I hate doing that. But it turns out like realistic examples of concurrency don't actually fit on slides. So here's a really dumb example of an algorithm. You have an algorithm that returns a future of an integer. By the way, who has used promises and futures in here? Okay, a lot of people. Who has used promises and futures from the Boost library? Some of you. Okay. There's some extra features in the promises and futures in the Boost library, which makes them slightly less broken than the ones in the standard. We'll talk about that a little bit. Okay, so in an asynchronous algorithm, the first thing you do is you create a promise, you get a future from that promise, now you launch a thread, and the thread is actually going to be doing all of the work for you, right? Eventually in that thread, you set a value on the promise. That's going to make sure that the value is available in the future. Now you detach that thread so it goes off and it executes, and then you return the future. By the way, don't ever detach threads. It's a really bad idea. It's almost always a bug in your code. Again, this is slideware. I apologize. Just go with me on this. So from main, what you're going to do is you're going to call this asynchronous algorithm. You get a future. And let's suppose that this is a boost future. So the boost future lets you add a continuation, right? So I can say future.then and give it a function. Say, when this, in a non-blocking way, when this future completes with a value, send the value to this other function. Give me back another future so that I can block when that entire aggregate computation is completed, okay? And the blocking call here is f2.get. That's going to block until the future is available. You can get the value out, and you can print it. Okay. Everybody okay with that so far? Okay. Great. So let's put that off to the side, and let's talk about what is actually happening under the covers and why this is slow. So when you create a promise future pair, you allocate some shared state. Right, so these things have, it's a communication channel, right? And it uses shared state so that the two different threads of execution can communicate with each other. When you are setting the value on the promise, and when you are attaching a continuation, these two things can happen concurrently, right? It's these different threads of execution, right? And when these things happen concurrently, you are going to be attempting to concurrently access the same shared memory. You're going to be reading and writing the value and the continuation fields in the shared state. Right? Concurrent access to the same memory is a race condition. That's bad. So that's why you have this mutex here, so that you can lock the shared state to avoid the race condition. Oops, sorry. Sorry. So you also need the condition variable, and you need a reference count because this is shared memory. So you have an allocation, you have a mutex condition variable, so you have locking, you have reference counting, right? And now the continuation, this is going to be some sort of a callable thing, but at the time you create this shared state, you don't know the type of the callable thing. So this is a type erased slot, like maybe a std function. If anybody has used std function, it uses what's called type erasure. So behind type erasure, you're going to have another allocation, maybe, and you'll have an indirection through a function pointer. So one or two allocations, an indirect function call, locking, reference counting. Like, how many other ways does this suck? Right? This is really heavyweight. Right? And if you build all of your abstractions, all of your asynchronous abstractions in terms of promises and futures, you are paying a high cost for doing asynchrony. Right? How successful would the STL be if all iterators did allocation and synchronization and type erasure? Right? We wouldn't even be talking about it today. Right? Nobody would use the STL if your fundamental abstraction were that heavyweight. Okay. So what can we do about this? Let's make a simple observation. This calling code in main, it knows what the continuation is even before it calls this asynchronous algorithm. By setting the continuation after that task is running in another thread, you are creating the conditions for a race. It's totally unnecessary. You could pass the continuation into the asynchronous algorithm. So attach the continuation and then schedule your work. All right, no race condition, that's great. So let's change our algorithm to take a continuation. So in this code, we're accepting the continuation. We capture it in the lambda that we pass to the thread function. And we do our work, and then when we're done, we pass the result of that work to our continuation. and then we set the value, which is the result of calling that continuation. It's real popular in functional programming languages. It's called continuation passing style. Okay, does everybody see how that works? Everybody see how we have removed the race condition on setting the condition variable, on setting the continuation? That's like the key insight here. Okay. So let's make a less simple observation. So passing the continuation in avoids some of the synchronization overhead because it removes the race on reading and writing the continuation. You write the continuation before you launch the operation, so there's no race condition. We can achieve the same result by starting the async work suspended, giving it back to the user. Here is a handle to work that hasn't started yet. You are free to add a continuation and then launch it whenever you feel like it. Okay. That is sender and receiver is, fundamentally. So let's rework our example. So instead of launching the work eagerly, we're going to return back a handle to work that hasn't started yet. How do you do that? Well, you give the user a function instead of a result. Say, when you are ready, call this function, I will start the work and give you the result. Okay. So your asynchronous algorithms are now going to return lambdas. Lambda defers the thread launch. And the lambda itself takes a promise, right? You pass the promise in, right? The promise is going to receive the result. Okay. Now I did something cute here. Let's see, do I have a cursor? Okay. A teeny tiny cursor. I don't know if anyone can see that. Anyway, so I no longer hard-coded this to be a stood promise or a boost promise. I've kind of let that type float, and that's going to be important. So I return a lambda. It takes a promise, captures the promise in another lambda, which you pass to the thread. That becomes a thread function. That does its work, sets the answer of the computation on the promise, and you're done, okay? Everybody see that? Okay, now we can imagine that this lambda that takes a promise, we can call that a lazy future. Okay. Right, so one thing I missed talking about here is since we're returning a lambda, you can't say f.then anymore, right? A lambda doesn't have a then member function, so instead we rewrite it as a free function called then, and it takes the lazy future and the continuation, and it does something, right? Then is just a generic algorithm, okay? So let's write then. Then is a function that takes a lazy future and a continuation. And it is going to return a new lazy future that is the composition of those two things. So since it's an algorithm that returns a lazy future, it has to return callable, a lambda that takes a promise. At some point, it's going to actually launch that task that you have passed in, that lazy future. And the task, we just said, is a lazy future, so it is expecting a promise-like thing. So let's gin up some promise-like thing that contains the logic of our then algorithm. So as a promise-like thing, it's going to have a set value, and it's going to have a set exception member, just like stood promise does. Now, what do these things do? Well, this promise is going to capture the state. It's going to capture the passed-in function, and it will also capture the inner promise. And then in this set value function, you're going to call set value on the inner promise after having passed values through the continuation. Just like we did with the async algorithm on the previous slide. And set exception, you just pass the exception value through. That's it. We've just implemented future.then non-intrusively as a generic algorithm on lazy futures. That's pretty cool. Notice here there's no allocation, there's no synchronization, there's no type erasure. It's all goodness. Okay. So in our original code, we then blocked and we called printf with the result of our computation. So what do we do now? Well, we could chain another continuation that does the printf for us. Okay. And then we actually have to launch this operation. All we've done is created a bunch of lambdas. Okay, so we actually need to call the lambda to launch the thread and go. So we can call the lambda with some sync promise-like thing, which just has a set value that does nothing and a set exception that terminates. And now this task launches and it goes off and it does its thing. Okay, great. There's some problems here though. Oops, we're printfing in the wrong thread. Okay, we're now printfing on the thread that was created in the asynchronous algorithm instead of on the main thread. It's kind of a problem. Bigger problem here is that we're no longer blocking. So when you call this last line of code that calls F3, right, you're going to tell this algorithm, okay, launch another thread and go do that work, and then main is going to exit, I'm done. Right, oops, undefined behavior. So we have to implement blocking. No problem. Blocking is just an algorithm too. Okay. So let's implement blocking. Let's call a sync wait function, parameterized on the type that you're expecting to get back. And it's going to take this lazy future, this task thing. Okay. You define some state. This is like the shared state in the promise future pair, except we get to put this state on the stack. We don't need to dynamically allocate it. And then we create a promise that just holds a pointer to that state, and we launch the task with that promise. Let's look at the state. Real simple. It's a variant. You could either have the value, or it can have the exception. And it starts empty. That's monostate. You also have that condition variable in the mutex. And the promise has the set value and set exception methods. And it sets either one or the other slot in the variant and signals on that condition variable. Okay. These functions, set value and set exception, are what's going to get called by our asynchronous algorithm when it has finished running. Okay. That's why then we notify on the condition variable, I'm done. So then our sync wait function just has to wait for it to finish. Right? We've launched the operation. That condition variable is going to get notified when all the work is done. So we just wait on that condition variable until one of our slots in the variant has actually been filled. And then, depending on which slot has been filled, I either have the answer to the asynchronous operation, or I have an exception because it failed. So if I have an exception, rethrow the exception. If I have the value, return the value. Okay. So great, I've just written future.get as a generic algorithm over lazy futures. So let's rewrite this to use sync wait. So now this is what our main function looks like. Okay. All right. Not bad. This asynchronous algorithm, let's look at it again, because it's got too much going on, right? Why is it launching a thread? Why is thread creation the responsibility of this asynchronous algorithm, right? So let's factor it out. let's create a function called newThread, and it returns a lazy future. And all it does is launches a thread and then immediately completes by calling setValue on the passed-in promise. That's it. Its sole responsibility is to create some sort of a execution context and then complete immediately within that execution context. And now we change our asynchronous algorithm to accept a lazy future. This is like the predecessor operation. And I use our generic then function to chain work. This is the body of my algorithm is now a continuation on this predecessor operation that the user is going to pass in. Okay. And now their main function looks like this. I create a new thread task. I pass it into my asynchronous algorithm. Now I've parameterized my algorithm on execution context. Now I can use my asynchronous algorithm with any sort of execution context, a thread pool, but anything. Right? So what happens now is I create this lambda, f. I chain work to it, f2, and now I launch it by calling sync wait. And what's going to happen is a new thread's going to get created, work is going to get scheduled, there's going to be a continuation that's scheduled after that, and then I'm going to block and wait for it all to finish. Okay. New thread is what I call an executor. It is a lazy future whose sole responsibility is to create some sort of an execution context and immediately complete in that execution context. Anybody who's been following like standardization committee work might know that there has been an executor's proposal that's been working its way through the committee for about 5 years now. Right? And we're finally getting around to this point. Like, okay, this is what we think an executor is. Okay. Great. So, lazy futures have quite a number of advantages over eager futures, stood futures, right? They can be composed without allocation, without synchronization, no type erasure. You can compose asynchronous operations generically, and you can even write blocking generically as a generic algorithm. Okay. Has anybody done any generic programming or played with C++20 concepts? Well, a couple people. Okay. C++20 is coming. Concepts, major language feature in C++20. It'll let you express in code type requirements of your algorithms. Okay. So let's define these concepts. Let's say that there's a lazy promise future, and it has setValue and setException on it. Okay. This is C++20 code that codifies in the language what the requirements of a lazy promise are. Okay. For reasons, we also want to add a setDone method. That is, when an asynchronous task gets canceled, right, there's going to be some amount of work that's chained onto that operation that is waiting for either a value or an error. Right? If work is canceled, then neither a value nor an error is going to be propagated down that chain. Right? You might want to let your downstream users know who's waiting for values or errors, that they're not going to get either a value or an error. So we add setDone to the method as a way of saying, like, hey, this work is being canceled. Do whatever cleanup you need to do. Okay. Now, maybe not everybody uses exceptions. I know, it's shocking. Right? So maybe we parameterize our lazy promise concept on an executor type, and we generalize setException. Now we call it setError, and we pass the error through. That's simple generalization there. And let's rename it. Let's call it receiver. And then let's do like a really quick refactor. Let's just say a receiver is something with setError and setDone, and we could say receiver of which takes our values. It's a receiver of these value types. And a receiver of value types is a receiver, and it has a set value method that takes those types. This is the concepts that we are considering adding to the standard. Okay. And lazy future is something, it's a two-parameter concept. Nothing is behaving as a lazy future unless you are actually like passing a receiver to it to execute it, right? And in the code that we showed before, it was an invocable thing to which we pass a receiver, right? Like the lambdas that took lazy promises, okay? So this is what the concept looks like. It's just an invocable thing that takes a receiver. And for various reasons, we're thinking of not calling it, using an invocable syntax. We're thinking of creating a customization point for it called submit. So you are a sender if you support submit. That takes the sender and the receiver. And you say, go. Okay. And we might call that concept sender to, because you send things from this to that. So it takes a sender and receiver. And a sender might be, the sender concept is probably just like something that you're going to have to opt into to let the type system know, like, hey, I'm a sender. Okay, that's what the concepts are going to look like. So another banner feature in C++ is coroutines. So whatever asynchronous abstractions we come up with, we want them to work really well with coroutines, because coroutines, we think, are how people are going to be expressing asynchrony in C++ 20 and beyond. So let's look at an example coroutine. Say you have this coroutine type called task. You have an asynchronous algorithm. You've got an asynchronous helper. This asynchronous algorithm just calls your asynchronous algorithm, co-awaits the result, then uses the result. Has anybody played around with coroutines? Yeah, okay, some people, maybe about a third of you. Coroutines kind of break your brain a little bit because they make synchronous code that looks synchronous asynchronous. And how does it do that? It does that by turning your function into callbacks. Like, okay, I wrote this really pretty function. It's a nice function. Compiler's going to rip it all to pieces, turn it into callback hell for you. You don't have to worry about it. Okay. Everything after a co-await expression or a co-yield expression is a callback. That's you suspend the state of this function, and then when that function gets resumed, you call back, and then you begin executing there. That's not an analogy. That's like actually how the compiler implements it. It breaks the function up into multiple functions. Well, receivers are actually callbacks too, right? So if a suspended coroutine is a callback, and if callbacks are receivers, then coroutines are receivers, and awaitables are senders. And that's not just like an analogy. It's like really, like we can make it so in the code so that anywhere you could use a receiver, you can use a coroutine, and anywhere you can use an awaitable, you could use a sender, and vice versa, right? So somewhere in a future version of the standard library, I hope there's going to be a function like this. There's an operator co-await that turns any sender into an awaitable thing. So if you write a sender, here's my submit function that takes a receiver, right? And if that's all you write, you should be able to co-await that thing in a coroutine without typing anything extra. And this is the glue that's going to make that happen. Now I could go through the implementation of awaiter sender. I have slides for it. It actually fits all on one slide, but it's rather dense. And if you don't actually are familiar with coroutines, it doesn't make a lot of sense, so I'm going to skip it. But what I will say, I'll show a little bit of code that shows the implications of this, right? So imagine we have some dumb sender, right? And it has a submit function, and all it does is send 42 to the receiver. Okay. And we have some asynchronous algorithm, and it accepts a sender. But it's a coroutine. No problem. I can co-await that sender in my coroutine and get the result. So I co-await it, get the result, it's 42. Okay. Because senders are awaitables, and awaitables are senders. Right there. Also, this is the sync wait function that we wrote earlier. Sync wait function doesn't know anything about awaitables. It knows about senders, but I can pass an awaitable to that function because an awaitable is a sender. All right, all awaitable types satisfy the requirements of the sender concept. So if I write an awaitable type by giving my type an operator co-await, I can write a receiver, like I can write an explicit callback and say, instead of co-awaiting this thing, I actually want you to use this callback instead. Right? So I can submit that awaitable thing with a callback. Cool. Here is the code that makes that happen. Right? So somewhere in the standard library of the future, I hope there to be this overload of the submit function, which takes an awaitable. And I'm going to create a lambda, which is a coroutine that gives a coroutine frame for the evaluation of this sender, of this awaitable, I mean. Co-await the awaitable in this lambda, send the result to the receiver's set value. Okay. This is what makes awaitables senders. It should just come out of the box. And that's this extra little promise type that makes that happen. Okay, so senders, awaitables, coroutines, receivers, all the same thing. Okay, so what else can we do with senders and receivers? Well, we've already seen that you can build generic algorithms on top of it. We've built sync wait. We've built then as generic algorithms. You can also build wait for all, wait for any sort of reactive programming library you could build on top of sender receiver. You could build eager promises and futures on top of sender receiver. You could build channels, asynchronous ranges, reactive streams. Let's look at futures and promises. You can build eager futures on top of lazy senders with no overhead beyond that which is inherent in eager execution. So you shouldn't have to pay for allocation and synchronization unless you need it, right? Unless you actually need a future that has that is a handle to work that started eagerly. So at that point, you should pay for that allocation. So let's see what that code looks like. Let's create your own future type. And the constructor of my future takes a sender. And in the constructor of this future, you have to launch this operation, right? Because this is an eagerly, this is a handle to eager operation. So launch this task. I have to pass it a receiver, so I have to gin up some sort of receiver for it. So create some shared state. I use that state to create a receiver. And here's what the state looks like. This should start to look a little familiar. Okay, there's a mutex in there. There's a condition variable in there. There's a get function that's going to be locking that mutex and then waiting on the condition variable. Just like in our sync wait function. Okay? And here's what the receiver looks like. As before, we've got set value, set error. We also have set done. Set done in this case is going to turn a cancellation into an error. It's just the choice I made here. But I mean, this is exactly like our sync wait function. Right? So I can build promises and futures on top of sender receiver very efficiently. just as if we were implementing the sync wait function. So eager interfaces, you can build eager on top of lazy without additional overhead, but you can't do the other thing, right? You can't lazyify an eager operation while also removing its overhead, right? So if your primitives are promises and futures, then you can't build sender receivers on top of that efficiently. But we have to do it the other way around. Sender receiver is the most efficient thing, right? So lazy operations are more fundamental than eager operations. Okay. The optimal way to eagerify a lazy operation depends on a lot of things. So there should be many algorithms like this. All right. So far we've been talking mostly about concurrency. What about parallelism? Now, unfortunately, we don't have enough time for me to go into detail with how sender-receiver supports parallelism, but I'm going to wave my hands at you and sketch, paint a little picture for you how parallelism is supported by sender-receiver. Now, remember this slide from earlier in the talk. Why are the parallel algorithms fast? Right? Because they let the user communicate to the scheduler information about the lack of cross-task dependencies. So in other words, it communicates the full structure of the algorithm's task graph to the scheduler before launching the tasks, right? And that's the key, right? So sender-receiver, imagine you have a non-intrusive parallel fork algorithm that, like then, creates a node in a task graph of senders, right? By composing the lazy senders, you're building a representation of the task graph that before it is executed, right? Independent of its execution. So anyone who has used expression templates in C++ or is familiar with expression templates knows that what you do is you compose operations to construct a tree that represents this operation without actually executing it. And then you can pass this entire tree off for evaluation as a whole. Now, the evaluator function might choose to evaluate it as you've specified, or it might reorder the tree and evaluate it in a more optimal way. But here's the key, right? You are creating this graph that represents your computation and then handing the whole thing off in mass. Right? Lazy execution lets you do that, right? It lets you create this lazy task graph and then pass the whole thing off. And if you pass that whole thing off to your scheduler and say, by the way, this represents parallel execution, there's no intertask dependencies here, then the scheduler has the opportunity to do something important, intelligence. So how the graph gets executed can then be left up to the scheduler. So lazy plus parallel is love, right? If you want to be able to do parallelism, you want to express your asynchronous computations lazily. So where are we now? It's very important that we design a system that does not only satisfy Facebook's needs or NVIDIA's, or that satisfies special case argument combinations for individual use cases, but one that cleanly generalizes for interoperation between different libraries from different vendors with different goals. And this is ultimately the vision of the STL, of Alexander Stepanov's realization that you can separate the concerns of containers and how your data is represented from algorithms, how you operate on the data. Right? And there's this piece in the middle, iterators, that can bridge the gap. Right? This is what we're looking for. We're looking for this piece in the middle that bridges the gap between your task graph and your scheduling. Right? And sender-receiver, this lazy representation of your task graph, is this glue in the middle. Okay, sender-receiver is a generalization of future promise. It accommodates eager and lazy execution, supports cancellation and error propagation, composes with low overhead, and it permits generic algorithms with efficient default implementations. Naturally accommodates executors as a special case of a sender. And it generalizes over concurrency and parallelism. So be lazy. So wow, I flew through that pretty quick. Any questions? Yeah.
Thank you for your talk. I have two questions. First of all, a question about resources. If I understood that we can use this concurrency model about concurrency now, how we can control resources? I ask about CPU in those cases. How I can control on which threads those tasks can be applied and worked. How we can control?
Yeah.
And second question, sorry, why sync waiter return movable or return move an object? Why move? I can.
Let me see if I can find that slide. Okay, so why this last line of code here? Return move. Okay, so you might be thinking that the compiler is going to be smart. This is a return statement. It should be implicitly moved. That is not the case if what you are returning is some complicated expression that is an L value expression. Okay, so in this case, you really do need to cast this expression to an R value in order to get move. Right? You're not going to get return value optimization here. Right? It's not going to kick in. And you're not going to get automatic promotion from L values to R values because this is too complicated an expression for the compiler to figure that out. Your first question, how do you control CPU resources? That was where we turned, separation of concerns. Okay, here. New thread is an executor in this model. This is how you control CPU usages. Right? So you might have another thread besides, another function besides new thread. Maybe you have a thread pool, okay? And you can have a member function on that thread pool called getExecutor. And it would return a sender that immediately completes by posting work to that thread pool. So you post the work to the thread pool, and then the only thing that that piece of work does is complete immediately by calling set value on the promise passed in. Okay. Yeah. Yeah.
Thank you for your talk. What do you think about actor model? It is an alternative to the futures, but you said that futures can be implemented over senders and receivers. How do actor model incorporates into this?
Well, my understanding of the actor model is pretty limited, but I think it works by message passing. And so it is like fully concurrent. You send and receive messages. So each actor needs a message queue, right? And inserting things into the message queue can require synchronization and allocation, right? So an actor model is something that would be layered on top of sender-receiver. I don't know what the details would be. I've never really implemented it. I could probably spitball something if we, find me in the discussion area later and we could figure out like how you might implement actor on top of sender-receiver. It's an interesting question. Yeah.
Thank you.
Thanks a lot for the great talk. Several questions, some simple ones. First of all, you started that shared state created between future and promise has several values, and assignment to values fields. Those fields has to be synchronized with an example that from the task you set the value, and from the calling side you set a continuation, right? But those are independent, and those are set in different threads. So why is this a race?
So that's a good question. Let's go back to where the code is here. Okay. So the first thing to realize is then is implemented by implicitly creating another promise future pair. Okay. And then is going to be setting the continuation field. Okay. Whoops, what happened? Where'd it go? Oh, there it is. Got it. So when in this asynchronous algorithm, you are calling setValue, what is going to happen in that promises setValue is it's going to check to see whether the continuation has been set, and if so, pass the value to the continuation. Yes? Okay. So there is the shared access to both the value and the continuation, right? And then when you set the continuation, you're going to be checking to see whether the value field has been set and send the value to the continuation.
Okay, makes sense. Thanks. Sorry, another question. It's concerning this generic algorithms. Well, for instance, sync wait. And when you wrote sync wait, you explicitly specified the return type.
Yeah.
While it should be actually known from the promise-like thing passed inside. So is it necessary to explicitly specify return type?
Right. So that's a really good question, and let me get to some code to show you why it's not. Let's see. Okay. Why it's not immediately obvious what the type is going to be. So here is an example of the asynchronous algorithm, and this is from earlier in the talk when we were just returning lambdas. Okay. There's no way to ask this lambda, when you call setValue, what is the type of the thing you're going to pass to setValue? Right? The lambda doesn't have that information in its type. Do you see what I'm saying? There's no way to introspect into the lambda to find the call to setValue and figure out what its argument types are. Now, you could give users a way to decorate their lambda with that sort of type information. And in fact, later on in the talk, I didn't call it out, but let's see. That's not it. This is it. Okay. All the way at the top, see here, I'm imagining that there is a utility called sender of. And there you can decorate a sender with compile time information. Like Scout's honor, I am going to be passing an integer to the receiver's value channel.
I'm sorry, really stupid question. I see this. Async algor returns core task of int.
Yes?
So you pass something into sync await, which explicitly says to return something of int.
Yes.
So it seems really transparent on this slide.
In this slide, yes, it's really transparent. Yeah. And so what we are doing in the standard is we are defining a refinement of sender concept called sender of. That is a sender that says what its associated types are. So there will be a version of sync wait that works with senders. And there'll be a version of sync wait that works with typed senders. Typed senders are the senders that declare their associated types. And so if you pass a typed sender into sync wait, you won't have to say what its return type is, because the sender will tell you what its return type is. Okay. But we are not requiring everyone who authors a sender to provide that information.
Okay, makes sense. And the last question, you've said that this is, sorry guys, that this is not like official position of the committee.
No.
So could you please elaborate a little bit what are the differences with the official position? and the plans?
Oh, well, when I say official positions means like nothing has been voted into the standard yet, right? So there's a committee meeting next week. For the very first time in the executor's proposal, we have sender-receiver, which is great. That's huge progress for us. It's something that still needs to be litigated in committee before we agree, like, yes, this is what we want. Yes, this is how we want it. And we're going to ship it in C++ 23 or 26 or whatever. So it's not official yet. There's still plenty of time for folks to argue about this. Yeah.
And thank you for your talk. And the question is, what is your take on structured concurrency? So is it going to be in the standard, or is it going to be in libraries?
Oh, so did you see Lewis Baker's talk at CPPCon on structured concurrency?
Well, there's probably multiple flavors of them, but what I mean is the way to structure coroutines into, say, groups so they can be launched or canceled in a, say, structured way. And so, like, we don't leak coroutines
Yes.
unexpectedly.
Yeah, yeah. I am a huge fan of structured concurrency. It really helps with the lifetime issue. I'm not a huge fan of shared pointers. Folks who do concurrency tend to use shared pointers a lot because they use unstructured forms of concurrency. And that when you don't have structured concurrency and logical join points in your asynchronous task graph, then you end up with detached computation, or computation whose asynchronous lifetimes do not nest. And when the asynchronous scopes of your asynchronous algorithms don't nest, then you have a really hard time reasoning about your code and ensuring that resources get cleaned up when they need to be cleaned up. So algorithms like wait for all or wait for any, these structured concurrency abstractions are going to be very important. And we think that they are probably going to be mostly in the library, but we do think we'll probably need some changes to coroutines in order to support things like asynchronous RAII, is something like an asynchronous destructor, but not making destructors asynchronous. Yeah, we'll probably need to add something like that to the language.
Hi, thanks. Is there an idea of let you express the composition of asynchronous futures in a nicer way than just to say then or when any or when all? So have a new operators such as on dot, such as on pipe, such as, you know.
Mm-hmm. So what's the question?
The question is there the idea of having such a special operator to express this composition in a more nice way?
Yes. Right, because when you do composition using functions, things nest awkwardly, right? And this is the problem I had in designing the ranges library. It's the exact same problem. And so you can solve the problem the exact same way. In fact, we have a library that uses pipe syntax. So you create a sender, and you can pipe it to then with continuation, and then another pipe then, and then another continuation, right? And then you get to compose your operations and read them from left to right. There have been various proposals for adding maybe something like a dedicated operator to do that sort of composition. I don't know if that's going to get any traction. I find that the pipe operator works fairly well.